Today, Ronert and me, we want to share our experiences and best practices about PySpark. Before starting with the presentation, it is noted that this presentation is actually intended for very experienced and immediate to experienced audience. So we expect from you some kind of experience with PySpark and Spark in general. This is a plan for today. So first of all, I will give a short introduction into PySpark. Then Ronert will talk about data structures and configuration and performance. And then I'm going to talk about unit testing with PySpark, data pipeline management, and then Ronert will give an example about how you could use the streaming API in PySpark. And finally, I will talk a little bit how you're able to put your models into production. So what is actually PySpark? I mean, if you attended the earlier session with Jose before, you probably know this graph, so I will go through this very quickly. Well, in a PySpark, what you actually do when you start a PySpark application, you actually create a Spark context, and this Spark context actually uses Py4j to create a JVM. On the masternode, and on the masternode, the JVM actually invokes Spark workers on the remote machines, and this remote machines actually starts the Python subprocesses and uses pipe to communicate with them. As already said in the last presentation, from this graph, you already can see that in comparison to Scala or Java, there will be also additional costs incurred because every time you start the PySpark application, you actually have to also create the Python subprocesses. So there will always be additional time involved with this. Another important point is actually that serialization happens in both the Python subprocesses and also the JVM. This is also an additional cost. Another important point, I don't know if he already pointed this out, is actually the Python memory allocation is actually not controlled by the JVM. So, for example, if you have very reasonable settings in yarn and something like this, that makes totally sense, you would still get some out-of-memory error because of this situation. But this is something that Ronert will go more into detail.
Yeah, let's quickly review some of the core data structures in Spark. So first of all, there are RDDs. These are resilient distributed data sets. And what they do is these are really a distributed collection, fault-tolerant collection of items. And they're a lazy data structure. And there are two kinds of operations on those, transformations and actions. Transformations are always lazy. They only get executed once an action is performed on them. And, and that enables Spark to chain operations together and run optimizations on those. Next up are data frames. Data frames are built on top of RDDs. They are essentially a collection of rows with some schema information, and these are mostly kept in the JVM. And once you perform PySpark API operations on them, all those operations get compiled to native Java bytecode, which is a huge performance boost. And a notable exception is Python UDFs. So if UDF is a user-defined function, and if you execute those user-defined functions on a data frame, what will happen is what that talked about. The Py4j has to communicate with the JVM and start serializing and deserializing objects, so it's a lot slower again. And that's why you should always use native Python objects. Native function calls on these data frames whenever possible. And one last tip when using data frames is you should always use the Hive context and not the standard SQL context. You don't even need the Hive installed to use this, but you get a lot more window functions and a lot more functionality in general. And yeah. This is a benchmark comparing RDD performance to data frame performance. And what you can see here, when you look at the RDDs, Scala is actually a lot faster than Python. Whereas with data frames, all the various APIs, they have exactly the same performance. And that's because what I talked about, the compilation to native Java bytecode. Now, another advantage of using data frames is that you get this nice succinct syntax here. So in most cases, whenever you can use data frames instead of RDDs, you should use those as much as possible. Then there is a third new data structure in PySpark and Spark in general, data sets. These came in Spark 1.6. They will actually be merged with data frames in Spark 2.0. They're statically typed. They're essentially data frames, but they're statically typed. It's an idea taken from the Apache Flink project. And what that means is that restricting the space of what can be expressed further enables many more optimizations, similar to what the MPP database is able to do. It will speed up Spark a lot. Now the problem is Python is of course not a statically typed language, so it's unclear yet whether we will even get to be able to use data sets in PySpark. And maybe, as Jose here in the front row proposed earlier today, we will end up having to use the Scala API if we want to use Spark to its fullest. Right. Okay, and the most difficult part actually of at least in our experience of running Spark is configuration and performance tuning. And there's not a lot of material regarding running PySpark on a real production cluster out there. So we want to give you some hints on how to configure Spark. Actually, my speaker notes are not working, and there's a lot of math here. So let me just try to fix that. 1 second. No. Give me just one. Okay, this is here. This is now. Okay. That did it. All right. So when configuring Spark, there's actually order of precedence. The place where there's highest precedence when configuring Spark is if you set it programmatically during your PySpark script. So if you run spark-conf, it overrides all of the other settings, both the options you pass in the command line and the options you pass in your configuration scripts of Spark. Second is the command line. So the command line overrides anything that you set in your configuration files. And finally, you have your configuration files, your Spark defaults, and Spark env. The most difficult part of configuring Spark is Spark memory management. Now, Spark has 3 memory regions. There is Spark storage memory. This is where all of your cache data resides. Then you have executor memory. This is where spills and shuffles and so on have their temporary storage. And you have user memory. This is where you can store custom data structures like hash maps and things like that. And then there's reserved memory for the operating system. Now, before Spark 1.6, this was a huge problem because there was this barrier here between storage memory and execution memory. These were actually separate memory managers. So if you have a very long PySpark script or general Spark script, and some parts of your program require a lot of storage memory, whereas others require a lot of execution memory, there's always a trade-off. There's no dynamic change between the two. So if you have a lot of room in your storage memory, but you need more executor memory, there's no way to share that between the two. And also between programs, for every single Spark program, you had to optimize your storage memory fraction. Now this has gone away in 1.6. The boundary is dynamic now. There's a single memory manager for all of your Spark memory. which is really cool because now you need to spend much less time configuring your Spark memory usage. What for us Python users is actually bad though is that the Python memory is still outside of all of this. The Spark JVM does not control the Python memory. So even if you tune this perfectly, you still might go out of memory on in your Spark processes. And exactly. So now in 1.6, this whole thing has become a lot simpler. And actually, on the internet, I've yet to find a good, simple, worked example of configuring a Spark cluster for PySpark. So we spent a lot of time trying to figure this out. What are the optimal values? So I want to quickly walk you through a worked example of how to properly configure a Spark cluster to run PySpark. As an example, we will take a 6-node cluster with 16 cores on each node and 64 gigabytes of RAM for each node. The first thing we need to do is we need to set our basic yarn config if we're running this on top of yarn, as I think most people do. We set it to 61 gigabytes of yarn RAM to leave a little bit of room for the operating system. And we also leave one of the cores for the operating system and associated processes. And next up, we actually need to do the Spark configuration. Now, it's a fairly good idea to overcommit your executors by about 1.5. And this is to avoid underutilization of the cluster from network I/O and general hard disk I/O weight. And you actually get the optimal HDFS throughput. This has been benchmarked and measured by Cloudera with roughly 5 or 6 executor cores. So here, 4 times 6 gives you 24, and 24 divided by 16 from our 16 cores gives you this 1.5 overcommit ratio. Now, now, as I've mentioned before, the Python memory is managed outside of all of this. And each executor core has its own Python process. By default, this is 512 megabytes. So now you have to, when you configure your cluster, you have to keep in mind that you need to allocate memory for Python. So we have 24 concurrent Python processes on each of the worker nodes. So that leaves us with 11,600 megabytes of executor memory. If you don't keep this in mind, you may very easily get run into some mysterious out-of-memory errors if you run PySpark. Okay. Anybody has any questions? Yes?
Can you repeat the calculation for the 11,600 megabytes again?
Oh, so you have for each executor, yeah, you have you have 24 Python processes, right? So that maybe, let me see if this, this comes up. So you have 24 Python processes. Each of those has 1,200 megabytes of RAM by default, right? And then you have, for your JVM, you have 4 executors, and each of those executors gets 11,600 megabytes of RAM. So that gives you roughly 59 gigabytes of allocated RAM, which is a little bit of 2 gigabytes of headroom for, you always should leave a little bit of space to avoid out-of-memory errors. Does that answer your question? Okay. And if you do need more of Python memory, so for simple data processing, 512 megabytes of RAM is enough. But there are some cases, say you're a multinational company and you want to calculate many parallel models for each of the regions you operate in using scikit-learn, and you're going to use your PySpark cluster to parallelize scikit-learn. Now, if you want to run scikit-learn, 512 megabytes of RAM is not going to be enough. So if you do run out of Python, out of memory errors, what you can do is you reduce the concurrency. And if you reduce your concurrency, you have less Python processes per executor, and then you can allocate more RAM to each of those. So in our example, if we reduce the whole thing to 4 executors per node with 4 executor cores, that leaves us with 1 gigabyte of RAM for the Python process, and a little bit less for the JVM. And we can keep reducing that. So we had some use cases where we left 4 or 6 gigabytes of RAM for Python if we want to fit fairly large models. Other useful settings we have encountered when running PySpark in practice is you can save substantial memory if you turn compression on. That's a simple true flag here. And if you run it on a cluster, especially a large cluster, you should turn speculative execution on. I really don't know why it's not the default. It just means if there's a very slow worker, it will relaunch that task for that worker on one that has some free CPU cycles. So then if you have a dying node or something, it will work around that. And finally, if you're using Python 3 like we do, there's actually a huge problem. If you're running it in a distributed environment, it will fail on operations like group by key, because Python 3 has a new security feature. It introduces a random hash seed for each Python process, and that throws off PySpark. So you actually need to set the Spark executor environment to some fixed hash seed. What about performance tuning? So one thing that you should never forget is to cache your RDDs you're going to reuse. And you always set these to memory and disk. I have seen no use case yet where it would make sense to do memory only and disk only. Be interested to hear if there's some use cases, but probably not. And say you're running you're using your PySpark cluster to run cross validation or grid search or something. You're going to reuse the same set of data many times. If you do not cache the data before you run your cross validation, what will happen is that Spark is not smart enough to figure out you want to reuse that data, so it's going to evict it from memory, and then you have to recompute all your features from scratch, and that takes a lot of time. So always cache your data. Avoid group by key on RDDs. It's super slow. It throws a lot of out-of-memory errors, and it's generally not a good idea. If you do need to group something by key, then use data frames, because they use this native JVM bytecode, and they're a lot faster for this operation. And finally, if you do need to run a grouped operation, like the scikit-learn models I was talking about in parallel, there's one feature that's new in 1.6 I don't think enough people know about. You can actually partition your data by key now. So if you load a data set into Spark, say from Parquet or something, you can tell it, okay, I know what key I will group this data set by at a later stage. So why not already distribute it over my cluster by that key? So if I do that grouped operation, there will be no shuffles at all. So that's a really handy tip. And finally, there's tree reduce, tree aggregate. You can use instead of reduce and aggregate, because if you run reduce, then everything will be sent to a single node, and this will become the bottleneck. Whereas using tree reduce, intermediate results will be spread amongst the workers. It's generally a better function. And finally, if you're using small data sets like a lookup table or something, always broadcast that so all nodes have that available. It's also can speed up your programs a lot. Okay, on to unit testing.
All right. So let's start with a little comic. Can you read this actually? Right. So as you can see, here's a PhD student with his professor, and obviously he's not a data scientist, not a computer scientist. So he wrote some code which is inelegant, which is messy, right? And actually, who of you had a PhD or did a PhD? All right. So maybe some of you know the situation, and this actually works quite well in academia, but in production, when you put your code in production or have a very huge code base, it's very difficult because you spend a lot of time in debugging your code. And actually, the solution to this is actually TDD. So who of you know what TDD is? Okay, so pretty cool. So TDD is actually one of the core practices at Pivot Labs. And well, I probably don't need to explain what it is, right? So you write your test first, write as minimum as possible code to have the test pass, and then you refactor your code. So far, this has worked pretty well for our software engineers, but in terms of data science, it is quite difficult. So the reality is difficult for us as well, because as a data scientist, there's some stochastic component in our work, right? Because when we start with a problem and we do some modeling, we are not quite sure whether we're going to use this model or not. And whereas as a software engineer, it's much easier because you know you broken an app, you know what kind of features you have, right? So writing things is much easier. And what we do is actually we divide our project in two phases. So we have an exploration phase and a production phase. And what we do in the exploration phase is we experiment with a lot of models. We use an IPython notebook, and then during this phase we also know what we want to test. And in the production phase, we're starting to put things into scripts, right? Because in the scripts you can use more automatically, and there we also start to write the test first. And for testing a PySpark application, we are actually basically just using unit tests and a single node Spark application. And one important note is that for testing, we're mocking our data, because this is what you actually do in unit tests, because the test should fail fast or very slow. This is actually an example how a test could look like. So this is a clustering example. So first of all, you convert your data frame, right? And usually in k-means, you probably also rescale your data, and then you assign your cluster. And then you can, like from the exploration phase, you know how the data structure looks like, and then you just collect, you have some kind of output that you already expected. And then what you do is you can implement the code like this way. So far it's just so minimum, because what you can do is you can take the variables from k and the seed and so on outside the function, so like refactoring your code. But this is a minimal code that would have the test pass. Basically, the whole example can be found on my repo. So if you want to check out, it would be cool if you're gonna check out it. Another important topic that I want to talk about is data pipeline. We had a data pipeline topic earlier. They actually wrote their own pipeline management. Anyway, so usually in the pipeline management, what we just saw before, it can be quite difficult, right? Because you have a lot of dependencies. Usually in a machine learning or in a data science project, you have different phases, right? So you get some data from a database, or you get data from anywhere, and then you process the data, and then you fit a model on that, and then maybe after the modeling, you will store your model on a database. And basically, for one project, it's quite okay, but when time goes by, you might have more projects and more use cases, and chaining all of them can be quite difficult. So what did we do in the past? In the past, actually, we wrote our own Python pipeline with Python, and in this case, we actually chained SQL and the PySpark code together. But one of the disadvantages of this approach is when you do Spark Submit on the master node, you actually have to distribute all your code to all the remote work machines. This can be quite a hassle because, for example, if you change a lot from your code, you have to do this every time and upload everything to your remote working machines. Oops. Another important point is logger. So logger is a module for logging. It's very powerful, but you can also spend a lot of time customizing it. So this is also not very good. So that's why what we did is we switched to Luigi. As an earlier presentation already said, Luigi is developed by Spotify. It's 100% Python code. It comes with a web dashboard. You have parallel workers. You have a central scheduler, and the cool thing is actually you have parameters, so you can pass parameters in each task, which is quite handy. So this is actually basically an example for Luigi tasks. So what you do is you import the Spark Submit class, and then what I just said, you can define some parameters like date and number of Ks, which you can actually pass to your script. And what you also can do here is you can set up your graph dependencies, right? In this case, for example, the feature engineering task has to run first before the clustering task can run. And basically, Luigi works like make. you make, but it's, yeah. And also, what we usually do in Luigi is we don't run it like all the settings programmatically or in the command line, but we set up it in the client config file, and then when you run Luigi, it will actually read all the Spark configs from Luigi. And with Luigi, it actually changed the structure. So when you do now Spark submit, you actually don't need to distribute all the Python or SQL script or everything in the Python path within the remote worker machines anymore, but Luigi is actually taking care of it. Of course, there are some disadvantages that comes with Luigi. So for example, you still have to use cron jobs to trigger your job, so there's no built-in. There are other things like Airflow, which does it, but it's not as lightweighted as Luigi. Another thing that I want to mention is that documentation could actually be better. So it would be cool if you have time and then you can also contribute to the Luigi project. And also, logging is quite okay in Luigi, so there's no much to do. But the problem is when you set multiple workers, you get a lot of logging, and disabling it's not really easy. And another thing is when you have a lot of tasks, because it's the nature of it, because you have a lot of probably use cases, something like this, you will have to duplicate all the parameters within the task. And for example, if you have one task, you have to take care also of this 100 parameters.
You actually don't, you just create a big task and you inherit from it, and that's it. I mean, from the Luigi part, you don't have to repeat the task, the parameters. You inherit from there.
Yeah, that's what I said.
Okay, so online learning with PySpark streaming. This is actually not a really how-to or in practice. It's more something I want to put your attention to. And this is something that's more recently came out in one Spark 1.5 and 1.6. And using Spark's stream processing primitives combined with online learning capabilities that came to the MLlib library, using some stochastic gradient descent-based methods, we can create real-time machine learning models that we can update on new data as it streams in and arrives. So at the moment, there's only streaming linear regression and streaming k-means, but there's more coming. And under the hood, it uses it's actually the code. If you pull it and have a look at the code base, it's actually fairly simple. It just uses for each RDD and map under the hood. And but this enables a lot of really cool use cases. So we can keep one model or a set of models always up to date on multiple, on new data as it streams in. So these models can quickly adapt to new situations or contexts. And another useful applications is to track the performance of the models in an online manner. And that enables you to, for example, run A/B tests with Bayesian bandit models or something like that in real time. So only if you have two recommender systems, and or even more, and you can evaluate them in real time. And as you monitor the performance, you only start to expose the best model to your customers. And this is like a real-time A/B testing and optimization with no manual intervention. And you can also monitor the model's performance in real time, so you can respond to changes if the performance starts to suddenly drop. One downside of online learning in PySpark and Spark in general is that the latency is fairly low. So you never get under 1 second latency using Spark. This is because it operates on mini batches and not on individual items in a stream. And that's why it's not really ideal to expose an API or something like this using Spark streaming. Flink looks very promising in that regard, but it doesn't have a very comprehensive Python API yet or machine learning library. Okay, on to operationalization.
Well, since we don't have so much time, we'll make it quite fast. So, so one of the approaches that we're actually taking is API first. So for everything that we do, we're trying to write an API as fast as possible. And to doing so, we are using Flask, which probably all of you know. And in this example, what we do is we train our model in PySpark, then we store it on Redis or for example, like, or you can also do it on HDFS. and then we write a predict function to make use of this model. And this is actually a very simple post method that we use to post the data, and then we import it from the request, and then we use the predict or assign clustering function to get the labels. This is something that we want to talk a bit more because so Flask is actually pretty cool, but you cannot use it into production, right? And for using things into production, if you saw the Palladium talk yesterday, they are using Marathon, and we are actually using Cloud Foundry. So Cloud Foundry is a platform as a service and what you can do is you just need your code. It could be any code, it could be Java, it could be Scala. You just do CF push. You define your manifest, which is kind of an instruction, and then you do CF push, and this will push it to the cloud and will take everything care from you. So it will take care of load balancing, updating your code, security, and many things. Actually, there's a trial version, so you can test it out for 2 months. And there's also examples how you could use Flask with Pivotal Cloud Foundry from one of my colleagues. So yeah, check it out. That's it. Thanks.
Yeah, sure.
Okay, so we have time for some questions. We only have this one microphone, so I would ask you to repeat the question so that they can be recorded. Sure. Over here.
Hi, you mentioned that Python can be quite slow compared to Scala and can be slow in the context of UDFs as well. Is it possible to get hold of the gateway and drop out of Python into Java or Scala and execute Java or Scala code directly for performance?
We haven't done that. I saw. Oh, sorry. Repeat the question. So the question is, Python can be slower, can perform slower when using PySpark, and is there a possibility to directly call Java code or Scala code, I guess from Python, right, to speed up processing? We haven't done that.
Yeah.
I saw a talk in PyData Amsterdam, though, from Holden Krakow. She gave an example of doing this, but I haven't tried it out yet. Yes?
Maybe as a follow-up question, so since we see there is some degree of overhead to use Python together with Spark, when should I say, okay, I had enough of Python and I should revert or use some different tool? Or use Python together with Spark only for the prototyping,
Yeah.
proof of concept phase, and then once I'm done, realize that I got to the limitations and hand it over to someone who knows Scala or Java or interact more directly with Spark.
Yeah. So the question was, when should you say, and I can't use Python anymore, I have to use Scala or Java due to performance reasons or features? Well, that's a hard question to answer. It depends on what you want to do and when you had enough. There's no hard and fast rules. I guess at the moment the performance difference is not that huge. Even if we go back to this benchmark here, even if you're using RDDs and not data frames, where was this here?
I mean, it really depends on your problem, right? So there's some features in Scala that you don't have in Python, and also it's a trade-off between speed of doing things and having the performance. So
even if you're using RDD, so in the worst case, I mean, you get about a 2- or 3-fold degradation in performance. I think that's fine, but things might change with the dataset API that's coming, right? It's going to be a lot faster, and we might not get that in Python. So then, yeah, we might actually have to switch to Scala.
Or if Dask gets more mature,
Or that, yeah.
we might switch to Dask. So
yeah.
More questions? Anyone? We have a new microphone.
Thanks for the talk. Have you considered on your unit test to use some fuzzing library to feed random data, or do you just use static data to test?
At the moment, we just use static data, but actually there is what is called this hypotheses library that comes from Haskell's testing framework, I would really like to have a look at that, but we haven't done that in practice yet.
Yeah, and we also have to figure it out because if you always use randomized data, you always have to change the output as well.
Thanks for the talk. I have a configuration question. For some reason, my driver starts on one of the slave nodes, not on the master nodes, next to the executor by default. Do you have similar problems or no? So I have to adjust cores for the driver and RAM so it fits on the executor.
What framework are you executing? Yeah, I don't have to repeat the question. What framework are you using? Is this on Yarn or on Mesos or?
Yeah, on Yarn.
You can just say no.
That's a
I don't really know. Stack Overflow is probably. Yeah. Sure.
So we haven't experienced it.
Okay. Are there more questions?
Okay.
You showed using unit testing. That's something I'm trying to do quite a bit as well, and
Yeah.
I found it's kind of non-trivial to get hold of a Spark context and to work with packages and stuff like that. I've been using Spark testing base, which in turn uses find Spark. But do you have any tips on how to get hold of the Spark context, how to make sure that packages work? I know there's like an environment variable you can supposedly set for IPython notebooks, but...
So what important thing is when you do the unit testing with PySpark, a very handy tip is actually also to shut down the logging. So like from logging from info to error, because when you use PySpark, you will get a lot of Java code and also a lot of Python traceback as well. So which is also important. And
but what you really want is here, that's a repo. There's a running example of. So if you use that, it will work.
Cool, thank you.
So actually, are you on a Mac?
Yeah.
Yeah. So actually, what you need to do is just do brew install Apache Spark, and then define the full path in the environment, and then just clone the repo, and then it's going to work.
Cool, thank you.
So there's a README.
Okay, I would propose that we start the coffee break, and whoever has more questions walks up to the speakers. So let's thank them again. And
thanks.
Thank you.